So let's say U1, U2, UN, these are capitals, so that these are sets. These are subsets of some vector space V. Then we define U1 plus U2 plus da 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 UN as U1 plus U2 da 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 UN, where U1 is in U1, U2 is in U2, UN is in okay. So let's think of an example. Let's say U is equal to 0, t, where t is positive, and V, let's say W is equal to S, 0, where S is 0. And these are both subsets of R2. Then, what's U plus W? Well, because U plus W is sum of U plus W, where U belongs to U and W belongs to W. That's the definition, right? And therefore, what does it mean to be in U? It has to look like 0, t, right? So U is like 0, t. What does it mean to be in W? Oh, sorry, I don't know why I put curly braces here. S0, okay, where T has to be strictly positive and S has to be 0 or positive. That's it. Now, graphically, let's see what this means. Here's R2. And what's the geometrical representation of U? Can you see it? What is U in that picture?
Y-axis above 0.
Y-axis above 0. So not including 0 is this guy. That's your U. Okay. How about W? What's that W? This time it includes 0 and it's here. Okay? And then, what do you get if you add these two? I should really write it here. If you add these two, it's simply S, t, with t being positive and S being non-negative, right? And when S and T are both positive, S and T could be anything, right? S and T could be anything, so they give you everything in here. If S and T are both positive, then they give you all the points in the first quadrant, okay? Now, is the positive y-axis included in here?
No. Or yes.
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 Is the positive x-axis included?
Yes. What? Oh, no. Wait.
Positive x-axis should be like this, right? To be on the x-axis, this has to be 0. Can t be 0?
Oh.
No, that's not allowed. T has to be strictly positive, so this is not allowed. So this set, the resulting set is really like, it's including here, includes here, but this is not included. Okay? That's what you get as a summation. Okay? Let me ask another question. Is U a subspace?
No.
Why not?
Doesn't contain 0.
It doesn't contain 0, 0, right? R2 is a vector space, but this is not a subspace. It's just a subset, right? Is W a subspace? It does contain 0, 0. Is it a subspace? If you have two things that looks like this, you add them, it's still like that, right?
Yeah.
However, does any scalar multiple of this again include in W? No, that's not true. For what scalar value can you choose to multiply this?
Anything negative?
If you multiply -1 to this, you end up with negative s, 0. In that case, this condition no longer works, right? So W is a subset of R2, which, you know, the three conditions for being a subspace, A and B is true, but the third one is not true, okay? So that's, both are not subspaces, okay? All right, so that's the concept. Now the question is, what can we say if we use this on subspaces? If U1, U2, Un are subspaces of V, then U1 plus U2 plus plus Un is a subspace of V. Let's try to prove this. Well, step one, I want to say U1 plus U2 is a subspace. Okay. We want to show that. Let's try to prove it. You know, it's wonderful if the proof is just clear in your head. That'll be nice. But if not, then you want to start with what you're given. Okay, what are we given? We're given that U1 and U2 are both subspaces, right? So let's write down what we know. Because U1 is a subspace, means three things. A, what's the first one?
Contains 0.
0 is in U1. B, if UV is in U1, that means U plus V is in U1. C, if, let me write C here. So there's some base field F and U in U1. That means C times U is. Same exact thing can be said of U2 being subspace. Okay. And then we know that A, 0 is in U2, B, UV is in U2, means U plus V is again in U2, and C, if C is in the base field F, and U is in U2, that means C times U is in U2. Now, we might as well, by the way, what I'm doing is actually quite wasteful, but I do want to show you in this longer way because I want to show you how we can manage to prove it without having to look at the textbook. The proofs in the textbook is somebody will first do a really messy proof and then try to figure out what are the only necessary parts and just use that, okay? It gives you a clean proof, which you can understand better, but it doesn't capture the thinking part. And that's where you need more work in, so I really want you to do this, okay? Now, because they're both same U and V, let's try to distinguish them by putting some subscripts here. So I'll put U1, V1, U1, V1, C1, U1, C1, U1. Over here, I'm going to put U2, V2, U2, V2, C2, U2, U2, C2, U2, okay? All right. So, these are the things that we do know is true. That's given. And from what's given, we have to show three things about U1 plus U2. Okay, what are those three things? Okay, A, so let's just put this in a box so that we can refer to it later. A, what do you have to show first?
0.
0 is in U plus U1 plus U2. Okay, how do you prove this? Well, look at the reference, see anything that's related to this. Which one's related to in here? The first one, right? So you write down 0 is of course in U1, okay? And how about here? The first guy, right? Okay. Put 0 is in U2. Now, what is U1 plus U2? U1 plus U2 collects anything that is a sum of something in here and something in there, right? Okay. So since 0 is in U1 and 0 is in U2, it's always this format. If you have star in U1 and something else in U2, then by the definition of what U1 plus U2 is, it's always that these two things have to be in U1 plus U2. Right? That's what this means, right? So that's the way that I'm going to write things down. So I have, this means that 0 plus 0 is in U1 plus U2, so that 0 is indeed in U1 plus U2. Done. First part is done. We've managed to prove 1/3 of showing that U1 plus U2 is a subspace. B. Next is, suppose, so what do I have to do? I have to say that if U, V are in U1 plus U2, then U plus V has to be in U1 plus U2. Okay. Now, this is a bit different. Here, you just had a statement to prove, but here you're given an additional assumption, and under this assumption with these two, you have to prove this final thing. You see that? Okay. You have to show under this condition and these two, you have to show this final thing. Alright, so let's do that. How do we make use of this? Well, to make use of this, you have to say u is equal to what? U is equal to if u is something in u1 plus u2, it better look like what? What are the elements in u1 plus u2? This is a collection of something in here plus something in here, right? So u is u1 plus u2, where u1 is in u1 and u2 is in u2. Okay? Now about v. Same thing. It must be v1 plus v2, where v1 is in u1 and v2 must be in u2. Okay? Then, what is u plus v? See, only because I've written this down explicitly what it means to be in here, now I can just confidently make use of this, see if what kind of conclusion we can get, okay? And the conclusion we can get is that we can say u plus v is equal to u1 plus u2 plus v1 plus v2. Okay. And now let's go back here and see what can be made use of. Of course, it must be related to this part B, right? So in here it says, oh, if you have u1 and v1 in u1, and then u1 plus v1 is in u1, and u2, v2 is in u2, then u2 plus v2 must be u2. Okay, good. So it seems like I have to put u1 and v1 together and u2 and v2 together, right? So let's do that. Sorry, u1 and v1 together, and then u2 and v2 together. Since u1, u2 are subspaces, okay, u1, u2 are subspaces, u1 plus v1 is in u1, and u2 plus v2 is in u2. Now the reason I'm writing this is because when we clean up the proof, we want to delete this, because this is something that we had to write for us to remember what's going on. But in the final proof, we're just going to kind of assume that we know, all of us know these two things. Okay? So since you have u1 and u1 and u2 and u1 and u1 and v1 and u1, since they're both in u1, their sum must be in u1 because it's a subspace. That's what I'm saying. Same thing in here. And therefore, since each one of these are in u1 and v1, I've shown that u plus v is indeed in u1 plus u2. Okay. All right, so now I challenge you to try part C. Okay, part C is if C is in F and some u is in u1 plus u2, then C times u is in u1 plus u2. Okay, again, this is a statement where you're given some conditions and then you have to prove this. Now, in addition to this condition, we know that u1 and u2 are subspaces, so everything I wrote here will be relevant. And really, you know that maybe the first two might be relevant later, but I don't think so. It's really part C that's relevant, right? So let's just delete these other ones. And try to use this to prove this. Okay? So imagine that you go home late and you're hungry and you have to cook some food. These are the ingredients for your food. Okay? You have to cook these up. Now, what's not so clear is, well, C is some real number. That's okay. What does it mean for U to be in U1 plus U2? That's not so clear. You need to rewrite this. If you don't know how to rewrite this, there's no more going forward. Okay, this will be an obstacle. So let's try to see what this is. Well, to see what this means, you have to think about what U1 plus U2 is. U1 plus U2, by definition, is a collection of U1 plus U2, where small U1 is an element of big U1, small U2 is an element of big U2. Okay? You should know this convention that we use capitals for sets and lowercase for elements. Right? It's a pity that I can't really distinguish well what's a lowercase and uppercase, but in the textbook they do that pretty well. So make sure you know this convention. So therefore, if U is something in here, that means U must look like this. Isn't that right? You get it? If U is an element of U1 plus U2, it better look like this. Is that good? Nod if you understand. Please nod. Okay? So, say, what is U1 plus U2? It's a collection of these guys. And to say that U is an element here means that U looks like one of these guys. So U must be equal to U1 plus U2 for some U1 and U2. That's what it means. Okay? Alright, so you have U equals to U1 plus U2. And once you've realized what that is, now you can forget about this. See, this is written like this, with U1 in U1 and U2 in U2. And make sure you know how to use this symbol. What does this symbol mean?
Is in.
Is in. U2 is in U2. Okay? This, or another way to say it is U2 is an element of the set U2. That's what it means. You have to learn how to use this symbol. Okay? In fact, when I'm grading proofs, if this is not properly used, I'll be taking points off. It's really important that you know how to use this, all right? Okay. And then everything else is kind of clear, like C being an F, that's clear. These, okay, so let's just keep going, okay. So, let's prove this statement. Proof. U is equal to U1 plus U2 for some U1 in U1 and U2 in U2. And now, what is CU? CU is equal to C times U1 plus U2, which is C times U1 plus C times U2. Okay? Now, C times U1 belongs to? U1, because that's what it says, right? Yeah. So in fact, I realized that you don't really have to distinguish the C's. Okay? We can let the two C's be the same. It can be this same C, okay? So we know that CU1 is U1, and CU2 is also in U2. So we can say that, let's say it over here. Save it here. Since U1, U2 are subspaces, okay, since U1 and U2 are subspaces, U1, CU1 is in U1, and CU2 is in U2. I'm saying this so that I don't have to make reference to this. See, this table was just for us to keep in mind what's available for use, I just used it and wrote it like this, okay? And hence, Cu equals to Cu1 plus Cu2 is an element of U1 plus U2. Now let's check this again. Does this really look like this? Yes, where U1 is Cu1 and U2 is Cu2. Right? See, you can call this one as U1, or maybe you don't. Okay, we can even rewrite this in the following. We can say just V plus W. That doesn't change the set, right? It's the same set. I only change the names, right? So now I can say this is V and this is W. That's correct because V is indeed in U1 and W is in U2, right? So therefore Cu is equal to Cu1 plus Cu2 is in here. Okay? So now that's true, and therefore, oh, this is done. So I've proved this step 1, okay? All right, so what should be the next step? Step 2, well, let's just move on. How would you show that U1 plus U2 plus U3 is a subspace? Well, we know that this is a subspace, right? So we can show that this is same as U1 plus U2 plus U3. Let's see why that's true. What are the elements in here? Can you write down the elements in this set? What are the elements in here?
Small u1 plus small u2 plus small u3.
Just like that, right?
Yeah.
Yeah. What are the elements in here? U1 plus U2 plus U3, right? Where U1 plus U2 is an element in U1 plus U2 and U3 in U3. Right? Anything that looks like this can be written this way. Anything that looks like this can be written that way. So it's the same set. Okay? So what does that mean? That means we can use induction. I already know that this is a subspace, right? And since it's a sum of these two subspaces, this is a subspace. And we can just keep going. The next one, you can just keep adding a subspace on and on and on, and eventually that proves the case for generality. Okay? Now let's make a note here. Note. Smallest subspace of V that contains all of these. And what's the argument? Well, if you have any subspace W of V that contains all of these, then because it's a subspace, if not subset. This is a subset, whatever it was an element. So if you have all of these as subsets in W, then because this is a subspace, you can take anything in here. That means all of these vectors that you choose from each of these subspaces are also elements of W, right? But then what does that mean? That means this has to be in W as well, right? Because being a vector space means you can take any subset, any vectors in there and add them up. It has to include it, right? Okay. But then, since everything in here looks like this argument shows that U1 plus U2 plus da da da, UN, has to be a subset of W. And since this is a subspace, this is like the smallest subspace of V that contains all the elements. That's the argument. Okay. I think the book has everything written down that way. I just didn't want to spend too much time on that. My more pressing need is for you guys to learn how to prove stuff. Okay, so here's an example. Let's say U is equal to x, x, y, y. And then V is equal to not V, sorry. Let's say V, it's okay, yeah. U, V are subspaces of R what? R 4. Okay, and we already wrote down a proof why this is a subspace. You can do the same thing here too. These are both subspaces. Okay. What is U plus V? Can you describe this as a set? Can you describe what R4 is? So what is U plus V again? U plus V is a collection of sum of two vectors, each from the subspaces. Right? That's what it means. And then we have to say something from U and something from V. What does that mean? Well, this means U is equal to x, x, y, y, right? And this means V is equal to x, 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 y. Now, are these general enough? Are these general enough? The answer is not. It's not. Why is not? Why is it? Is this not general enough?
Yeah, I thought you had to add subscripts
Why? Why do you have to do that?
because then they can be equal to each other.
Yeah, we don't need these two to be equal to each. If we just do this, then we are only considering sets of items that share the same exact coordinates for x. That's not what we're doing. Okay? So we better have subscripts to distinguish them. Okay? Now let's try to add them together and see what we can conclude from here. U plus V gives you x1 plus x2, x1 plus x2, y1 plus x2, and then y1 plus y2. Okay, what do we see from this? What kind of pattern or what kind of property does this final set satisfy? What do you see? Can you say anything about those kind of numbers?
Is it x comma x comma y plus x comma y?
So it's definitely, these are the same, right? X comma x comma. I mean, see, when you say x comma x, you're really saying x is x1 plus x2, x is x1 plus x2, right?
Yes.
But then to say that you better have, if it was y1 plus x1 plus x2, then what you're saying is right. You can say it's like x. But this only has x2, not x1. Right? Okay. So you can't say that. But you do see that the first two coordinates are the same.
Yes.
Right? How about these? Can these be arbitrary? Yes or no? Do you know the word arbitrary? Arbitrary means anything. Can it be anything? Yes, because, see, I can write any, so here, 1, 1, 3, 5. Can you make this work? Well, I guess I can take y1 as 2. How's that?
Mm-hmm.
Then y2 will be 3. This x2 should be 1, right? The x2 should be 1, so x1 must be 0. So it does work. Is it possible to do this for any number you choose, as long as the first two are the same? Yeah, right? Okay. So you can say that these look like x, x, y, z. Okay? Where, so that means u plus v is going to be sets of x, y, z, where x, y, z are real numbers. Okay? That's what you get. Now, some of you might still be puzzled. Really? How do you know that you can represent anything that looks like this into this format? Well, let's see. Let's just check. What am I trying to do? I'm saying x is x1 plus x2. Y is y1 plus x2. And then z is equal to y1 plus y2, right? For any triple of numbers x, y, and z, can you find x1, x2, y1, y2 that would satisfy this? Well, as a matter of fact, it's easy because you have four things that you can control to produce three different things. So in fact, you can kill off one of these. You can just say x2 is 0. You can still manage to make everything work with x2 equals to 0. Let's see how that works. If x2 is 0, that means x is x1, y is y1. And then z would be simply, so that means y2 has to be z minus y1. Okay? So the argument goes, it becomes a little confusing, but hear me out. Let's say somebody gives you x, x, y, z, any 4 numbers where the first 2 are the same. Then you can say, I can make that work as a sum of something from here and something from here. And the other person asks, really? How can you do that? Then your answer is, well, I'm going to have one guy to be x, y, now x, x, y, y, to be one person, okay? Oh, sorry. And then the other guy would be x, 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 and then this last, oh no, sorry, this should be 0, 0, 0, because I'm setting the, see, I'm setting x2 as 0, so 0, 0, 0, and then I'm putting z minus y, okay? Now, see what you get if you add them. You get exactly this, right? So, this is definitely from U, this is definitely from V. I managed to add them up to create anything like that, so I'm right. Okay? Okay. I probably should have done the following example. Let's say, so example 2. Let's say, in this case, U is just x comma 0 comma 0. So it's a subspace of R, which is just the x-axis. Now V, I'm going to put 0 comma t, where t is in R. Now the question is, what is U plus V? Well, the answer is rather simple. The answer is, if you add this plus this, of course, what do you get?
X.
Xt, right? And x and t in R. But what I really want you to think about is, what is the shape of U plus V? And in order to answer that, let's say this is x, that's y, that's z. Let's first think about these subspaces. So first of all, U is x-axis itself, right? Now who can tell me what V is? What's the geometric shape of V? At each point you have a point, right? So think about this as like a moving point on space. At time t equal to 0, where are you at? You're at the origin. Time 1 second later, where is this particle at? 0, 1, 1. Where is that? 0, 1, 1 is 0 in the x, but you go 1 in the y direction, 1 in the z direction, you're here. Right? So you're here and now you're here. Okay? Time t equals to 2, where are you at? 0, 2, 2. Right? So what kind of object is this?
1.
It's a line that's on which it's a line on YZ plane, right? Okay. So it's a bit hard to see, but see this is actually 90 degrees. So here's x, okay. Here's x, here's y, here's z, okay. The u is this x-axis itself, right here, and then the V is the YZ plane, and you're going 45 degrees that way. So it's like here, but this angle is still 90 degrees. Can you see it? You see it? Okay. Now the question is, what is the result of U plus V? It's this entire plane. Okay? It's a tilted plane. Okay? Because if you have x comma t, you're free to roam anywhere in the x-axis, you're free to roam anywhere in the y-axis, but you have to add the two, so it's like you're trying to get all these things where they meet. Okay? You draw, from any point here, draw a perpendicular line in this slanted direction. From any point in here, draw a perpendicular line here. The point where they meet, that's a point that can be described like this. Alright? So that's what U plus V is. It's a plane containing x-axis. And it's also 45 degrees slanted, and that one I'm too lazy to write. But what's important is this. We already know that U plus V is the smallest subspace of V that contains each individual ones, right? So here you're in R3, okay? What are the subspaces of R3? Give me all the subspaces of R3. First, the null space, the trivial vector space, the one with only the origin, okay? What else?
The set of all planes.
Set of all planes going through the origin, that's the subspace, dimension 2. Are there dimension 1 subspaces?
Set of all lines going through the origin.
Set of all lines that's going through the origin. Every line that's going through the origin, right? And here we're describing two lines that's going through the origin, right? What is the smallest vector space that contains both lines? The subspace, the plane that's containing both of these lines. Isn't that right? Okay? So that's what U plus V does. You need to have that kind of intuition when you see this U plus V. If you only think of U plus V as words, then you can't get very far. You need the intuition. U and V are these like lines and planes going through the origin, and then U plus V gives you something that's bigger than each individual ones that contain both. It's still some kind of a linear space, flat space that contains each individual ones. That's what U plus V is. Is that good?